Okay, so today we will continue on in our section on numeric methods, and we'll cover a whole bunch of root finding methods. Okay, and we left off on Wednesday talking about fixed point iteration. Okay. And the whole idea behind root finding methods is that, we have some function f of x, and we want to find, all right, let me have you guys settle down, please. We want to find where f of x is equal to 0. So the locations of x where f of x equals 0, these are our roots of x, okay? The roots of f. Okay, and so we first start off with fixed point iteration. And we said we have some function f of x, and we want where f of x equals 0, and we are going to kind of rewrite this. So we have basically g of x equal to x, and we find the g. Okay, so basically come up with a g of x so that solutions to g of x equal to x are also solutions to f of x equal to 0. All right. So here I'm using some examples from the textbook. This is example from chapter 10 in scientific programming using R. All right, or I don't know, I forget what the full name of the textbook is. Scientific programming for statistics using R or something, I don't know. Something like that. The link's in the course syllabus. And we start off with the function f of x equal to log of x. Log in statistics is always the natural log. Okay, log of x minus e to the negative x. Okay, so this is what we have. We've got log of x equal to e to the negative x, and we want to find where is this equal to 0. Okay, so if we set this equal to 0, we have a few things we can do to get, find a g of x, right? So now we're going to find g of x so that g of x equal to x also solves f of x equal to 0. So we will, so one option, option 1 is we start off with log of x minus e to the negative x equals 0, and then we move the e to the x term to the other side, e to the negative x, and then I exponentiate both sides. I say e to this and e to this, and so here I would get x equals to, I'm going to just write it this way, exp of negative x. Right? And so we could say g of x is equal to this. G of x equals exp of negative x. And we'll solve g of x equal to x. So that's one option, right? And solutions to g of x equal to x will also be solutions where f of x equals 0, right? Other options, option 2 could be, we've got log of x minus e to the negative x equals 0, and we could take this and do x minus this, so we have x minus log of x minus e to the negative x is equal to x minus 0. And we will just say this is equal to g of x. All right. We find where g of x equals to x. That will also solve the original one. Right? Or another option, we've got lots of options, and there's many ways to solve the problem. Is we could just say we can add x to both sides, and we can have x plus log of x minus e to the negative x is equal to x, right? And we'll call this g of x. So these are all just different ways to try this out. Okay. And when you look at these things, you can't really tell which one's going to work and which one's better than the other. Okay. The whole point of numeric methods was so we could avoid having to do some math, and we just wanted to have the computer solve the problem for us, and this doesn't really, we've got a few options here. And so as far as fixed point iteration goes, sometimes you might have different g of x's, and some of them will work and others will not. So in this case, you can't really tell just by looking at it, but option 3 will fail, and option 1 and option 2 both work. And option 2 happens to be the one that works the quickest. But let me just go over the kind of the algorithm for fixed point iteration, and we'll go over this. Okay, so the algorithm is that you take your current value of x, you plug it into the function g of x, and whatever g of x spits out, that's going to be the value you use for the next iteration of x. Okay, and that's it. This is the entire thing, and you just do this until it converges. Okay, so this works when kind of the absolute value of the slope of g of x at a fixed point is less than 1. Okay, and if it's greater than 1, it doesn't work, which limits a bunch of functions, but this is just how it goes. So let me just kind of illustrate this with a function here, or just a picture, not really a real function. All right, so let's say we've got some function like this, and I have okay, so this line represents y equal to x, all right? And we'll just start off, let's say right here. Okay, so this will be my x0. x0. This location up here is f at x0, right? And I'm going to come over and I'm going to say, all right, let's just draw a line over here. We'll go this way. And so this location right here, this is f at x0, right? And this spot right here, if I come down here, this will represent my next iteration of x. So I'm going to draw a line from here down to here, and this represents x at time 1. X at time 1 is equal, looking at this, is f at x at time 0. Okay, do we see this? from the picture. So this location of x1 is equal to where f of x0. Okay, and so I would continue this iterative process here and say, okay, I'm going to come over to right here, and I'll go down to right there, and this will be my kind of my next location at x at time 2, x2, and we can just imagine this whole thing kind of going back and forth until it converges right here. Converges here, and so that's what we have. Okay. All right. So visually, are we able to see the fixed point iteration working here? Okay, so basically, yeah, we plug in x0, we get f of x1, and that's going to become our new x1. We plug that in, and that's going to become our x2, and we just get closer and closer and closer until we converge to the point. I'm sorry, this entire time I've been using f, but I should have been saying g. My bad. Okay, and it's going to converge to where g of x equals x. And based on the way we've written g of x, a solution to g of x equal to x will be a solution to f of x equal to 0. Okay, just quickly, if I'm going to just draw a little picture. If the slope of g of x is greater than 1, then it will fail to converge. So I just draw a picture here. Let's say that's not a very good picture. Okay, so let's say we start here, and I start right here. Okay, and if I come up to here and I say, okay, well, where does the line cross? Where is the line equal to x? Then my next iteration will take me over to here, right? So if this is x at 0, then x at time 1 will be right here, and you can see that this is going to diverge. This will be x1 and x2, and this diverges. It's going in the opposite direction. So the fixed point iteration only works sometimes, and it all depends on how you've written g of x. So in pseudocode, okay, we can write a function, fixed point will be a function of, we need the function g, and we need some initial starting point x0, and then we might have a tolerance value. The tolerance value, because this can continue on forever, the tolerance will be a point where, you know what, at my current iteration and my next iteration, the difference between these two values of x was really small, maybe like 1 million. Okay, and we say, okay, well, at this point, I'm going to just say x didn't really change, therefore we have converged. So, you know, your current value might be like 2.000002, and then at the next iteration it's 2.00001, and you say, okay, you know what, this is good enough, I'm going to call it a day here, all right? Rather than continuing to iterate, because at every iteration the amount you improve gets smaller and smaller and smaller. So So you might just say, you know, the tolerance is equal to something like 1 times e to the negative 6 or something like that. Okay. All right, so inside the function, we would set, maybe we'll start off with x old equal to x0, and then we will set x new equal to g of x old, and then we will create a while loop, and this will be while as long as the tolerance, the difference between x old, the absolute value minus the absolute value of x old minus x new is greater than our tolerance. Then continue the loop, and the loop, all it is that take your current value of x new, throw it into x old, and then reassign the new value to be g of x old. Okay, so we'll do that. We run that while loop, and at the very end, return your latest value of x new. Okay, does that that code make sense as far as how the function might run? All we're doing is we're just implementing this. We're saying xn is our old x value, and the new x value is going to just be g of x old. Good? Okay, so that's fixed point iteration. And again, it only works when the slope of g of x at your fixed point is less than 1, or the absolute value less than 1, and you have a lot of options for how we might write g of x. Okay, here's another method, another root finding method. Okay, and this one is NewtonRaphson method. Do you guys learn this in calculus? Does this sound familiar? NewtonRaphson method? All right, I asked the last class, and a bunch of them said they'd never heard of this before. But I saw some people nodding their heads. I also saw some people shaking their heads, but anyway. We'll cover this now, all right? Newton-Raphson method. Okay, how does this work? Well, let's draw a picture. This is like our best way. Okay, there's some function. Okay, and okay, so here's our function, and we want is this location right here, right? This is our root. We want this. Okay, and then, so we just start off with some point. This will be our x0. Okay, and we come up, oh, that's the wrong tool. We go up to the line right here, okay? Okay, and so this location, this is f of x0. And at f of x0, we draw a tangent line. Okay, so we draw a line tangent to the curve, something like this. I don't know, is that tangent? Tangent enough. Okay, and then we say, okay, where does the tangent line cross the axis? And this will be x1. So we start at x0, okay? Go to f of x0, right? Draw a tangent line there. And then x1 is the location where the tangent line crosses y equal to 0. Okay, and then so your next iteration is it's going to be right here. We'll go up to the line, and then I draw a tangent right here. I don't know what tangent line looks like right there. And then so this location right here, this will be x2. And you can just imagine this kind of going on continually until you go boop, 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 and then you get to the spot you're looking for, right? Okay, so visually, do we understand what's happening here? Okay, so then, what is this location, right? What is x1? How do we get this? All right, so let's take a look at this triangle right here, okay? I'm gonna look at this triangle. All right, and okay, so what's the height of this side here? I'm going to call this the rise. What is the height here? F of x0. Great. Okay. And okay, and here we have slope equal to rise divided by run. Okay, so what is run equal to? Run would equal to rise divided by slope, right? So we remember this from algebra? Yeah, okay. So we got, so the rise is equal to f of x0. What is my slope? Well, the slope is just f prime of x0. That's, sorry. Slope is f prime of x0. Yeah, okay. So, so if this is my run, then x1 is equal to x0 minus the run, which in this case would be x0 is, x1 is x0 minus the rise, which is f of x0, divided by the slope, which is f prime of x0. Okay? Or we generalize this, and we just say x at time n plus 1 is going to be x at time n minus f of x at time n divided by f prime at time xn. Is that okay? So we have, so this is the Newton-Raphson method, okay? We just say, we just continually update this until the next iteration is practically equal to our current iteration. Okay, let's, should we write some pseudocode for this also? We'll try this out. Okay, so the pseudocode here, we're going to need to write a function that returns both f and f prime of a certain value x, okay? All right, so let's say, just for simplicity, let's say f of x is equal to x squared minus 5, right? Or let's do x squared minus 4, okay. All right, and so when we write this, we would have to write f as some function of x that will return, okay, and we'll have fx will be x squared minus 4, that will return that, and then we'll have f prime, which will be 2 times x. Yeah. And what we return will be, we're going to just put these two together, f of x and f prime. Okay, Therefore, if I plug in f at location 5, f at 5 will return, a vector of 21 and 10, right? And then if we want one of these things, we would say f of 5 bracket 1, which will be 21, and f of 5 bracket 2 will be 10, right? So we can access these things like this. So it does require us to be able to take the derivative of the function, okay? So we do well, I mean, if we can't take the derivative, like let's say we can't figure out the math to take a derivative, what other option do we have? Like we have a computer, and we might be able to have the function. Can we do something? So what's the definition of the derivative? Okay. So basically what we can do is we can do f, and then we'll plug in x plus like a delta minus f of x. And then what do? We divide this by the delta, right? And then so we could just use, I don't know, delta equal to 10 to the minus 6 or something, right? We just use a tiny delta, and this will give us something that's pretty close to f prime, right? So if you can't figure out that the derivative of this is some function, you're unable to do that, you can kind of approximate it using this. Okay, so anyway, we have, and then so here's a kind of a numeric derivative approximation. So this will be like an estimated f prime. Okay. All right. NewtonRaphson then. All right. So we'll do NewtonRaphson will be a function, and it needs to be a function of f that returns both the function f and f prime. We start off with an x0, and then we'll need a tolerance, maybe equal to 1e to the minus 6. Who knows? Okay. And now what do? We say x old will be x0. And then I guess, well, we'll need to have some kind of while loop. Okay? And we might need to throw something here, but we'll have an absolute value while x new minus x old is, well, the difference here is greater than our tolerance, iterate through this, and we will just say x new is going to equal, what do we have? We have x old, so we had xn plus 1 is equal to x of n minus f of x0 divided by, I'm sorry, f of xn, f prime of xn. Okay, so we've got x old minus, and we're going to just say f of x old square bracket 1 divided by f of x old square bracket 2. Okay, so that will be f of x divided by f prime of x. Oh, and I'm sorry. First we have to say, we'll take our x new, throw it into x old. We update our x new by taking this, we calculate it, and then we just continue. We keep looping, and then at the end of that, it will kick out once this thing is smaller than the tolerance, and we will return x new. Okay. Does that make sense for how NewtonRaphson is? Okay. Any questions? All right. Well, then we'll continue on. So that was NewtonRaphson. NewtonRaphson uses tangent lines and requires us to have a derivative, or at least be able to kind of approximate the derivative. We've got something called the secant method. Similar but different. I guess that's everything. Okay, so here's some function. And the secant method, we require two starting points. Okay, so we'll start with a x0 and an x1. And the way this works is we draw let's use a different color here. So we'll draw, we'll calculate these two things. Right? So I've got f of x0 and f of x1. And we draw a secant line that connects these two things. So it runs through those 2 points. So it goes from there to there, and then it runs into the, what do you call this? Y equals x, all right? And this location will be our x2. Okay, so we do that, and then we continue on, and we say, all right, let's try this again. And come over here, and we say, all right, let's draw a line that connects these two. So it goes from x1 to x2, and it runs through there, and this will be x3. Okay, and then it just kind of, the lines continue until it intersects here. Does that kind of make sense? Okay. So we want to know, all right, how did we get, all right, so these were our two starting points, right? So we gave starting points, we had two starting points. So how do we get this? Okay, so I'm going to look at this triangle here. Okay, we'll look at this one right here. Okay, so x2 is going to be x1 minus the run here. Is that okay? All right, so what do we have? The run, if this is the rise, the run is going to be equal to x1 minus the rise divided by the slope, right? Is that okay? All right, so what is the rise right here? Okay, rise is going to be f of x1. Okay, and what is the slope of this hypotenuse? It's not f prime. We're not calculating f prime. Okay, it's not exactly f prime. The slope is actually determined by this and this location, right? This segment is what determines the slope. Yeah, is that okay? All right, and so if we look at that part, then we will have to use our definition of the slope, being this slope is rise over run of this triangle, right? Okay, so the slope will be rise over run of the smaller triangle, the upper triangle. Okay, so what is the rise of this top triangle? It's the difference between fx0 and fx1, right? So we'll do okay, we'll do f of x0 minus f of x1. Okay, rise, and then what's the run? Okay, it's going to be the difference between x0 and x1, right? x0 minus x1. Okay, or equivalently, we could have. It's also the same if we write it the other way: f of x1 minus f of x0. These are exactly the same, right? x1 minus x0. Okay, either of these. So that's going to be my slope. Okay, so putting this all together, I've got x2 is equal to x1 minus, I'm going to have rise, which is f of x1, divided by the slope. So I'm going to just take the slope and flip it over. I'm going to just say times x1 minus x0 divided by f of x1 minus f of x0. Is that okay? Everyone's okay with how we got this? Okay. And then so if we just generalize this, we're going to call this x of n and x of n minus 1 and so on and so forth. So secant method, I'm going to flip this slide. We have x at time n plus 1 is equal to x at time n minus f at x at time n times x at n minus x over n minus 1 divided by f of x of n minus f of x n minus 1. Okay, so you no longer need to find derivatives. Okay, so no need to find derivatives here. That's that's a nice thing. So that's the secant method. Interesting. All right, and writing the pseudocode is not. It's not any harder than writing any of the other things, right? You just set up a while loop, and then you just say the new value is going to be the old values, but now you have two old values. You have an x old and an x even older. Okay, maybe an x old and an x old minus 1 or something like that. Okay, so you just have two old values to keep track of, and you set it up that way. Okay, and then one more root finding method, and this one's called the bisection method. All right. So the other root finding methods that we've covered so far, they could fail if the function has some weird properties. They could fail. Like if you happen to get at a location where the slope is very flat, okay, then like your secant line can shoot off to somewhere. Right, like just imagine you get something that looks like this, right? And you want to find it, and then your 2 points go from here to here, then the secant method will take you like way far away. Okay, so that's a possibility. Okay, you don't. So the bisection method. So the bisection method, on the other hand, is guaranteed to work. As long as f of x is continuous. Okay, so as long as f of x is continuous, the bisection method will work. And I think it's very easy to visualize. You just have some, if this is your y equals 0 here, you got some function like that. You just start off with you have two endpoints, x0 and then an x1. Okay, so you kind of have two endpoints, and you just have to say the two endpoints need to take different signs. Okay, two endpoints, x0 and x1, and then the sign of f of x0 needs to be the opposite of f of x1. Okay, that's it. So you start off here and here. Okay, and then you say, okay, we're going to find a spot halfway in between. So x2 is going to be x0 plus x1 divided by 2. Okay, and then you say, okay, well, here's f of x2. Let's start off with f of x1. I got f of x0. And here I got f of x2. Okay, so you do this, and you say, okay, well, what is the sign of f of x2? And you say, okay, what's the sign of this? I will keep the one that has the opposite sign, and I throw away the one that has the same sign. Okay, so keep of the original two endpoints, keep the one with the opposite sign, throw away the one with the same sign. Okay, so right here we would throw away x1 and we'd say, okay, x3 is going to be halfway between here. And we would say, okay, f of x3. And then we would keep, so now we are down to here and here. And then we'd say, okay, x4 is going to be halfway between those two. And we continue so on and so forth. And we just keep dividing our region in half, and we just continue on forever. Yes, question?
Why does this only work if the range was negative?
What do you mean the range was negative?
So like, if it's an example like a parabola, it's only in the positive region.
Well, then you wouldn't have a zero, right? A root means it has to cross zero.
Yeah, no, but like it doesn't go in, like no y value is negative, but it's still.
Oh, I see. Right. Oh, so if the zero is tangent, okay, you're right. It will fail in that circumstance because you won't find a location where you have things of the opposite sign. So in that circumstance, yes, it could fail. But yeah, and in any other situation where you do have, if you start off with an x, if two x's and they have opposite signs, this is guaranteed to work. But you're right. If you have this, I can't. It's really hard. Okay, and it's just tangent right there. You're right. It's not going to work there. Okay, but other than that, this will work. Okay, and then so coding this up, basically you start off with two initial starting points, and then you just have to do kind of a, you'll have an XL for an X left, and an XR for an X right, and then you'll have an XM for a midpoint, and then you'll just basically do a check to see if you should keep the midpoint and the left point, or the midpoint and the right point. Yeah. So I guess you'll start off with so we'll have bisection. Okay. And okay, so then bisection, you'll have some function. Oh, we're gonna run out of time here. But basically, you have your f, you have your x left, and you have your x right. Okay, and then a tolerance value. And basically, you're going to just check for, we'll say FL is the function at x left, and FR is going to be the function at x right, and then you'll calculate a midpoint. So we'll have xm being xl plus xr over 2. And then you'll figure out, what is f of x? So you'll have fm, which is the function at xm. And then you say if, basically, you're going to do f left times f right, or not right, f middle. Okay, if that's less than 0, this means they have opposite signs, right? So what happens here? Then, so this is inside your while loop, okay? Or somewhere in the while loop. You got to put this in a while loop somewhere, okay? Basically, you're going to keep the left, okay? And the else, meaning that it's greater than 0, you would keep the right. Oh, no wonder. Okay. And you would work your code that way. Okay, we'll end here for today. This covers root finding methods, and we'll look at some applications of all of this, because I know it just feels like, why are we bothering with this? But but there are applications. Okay, we'll see you guys on Wednesday.